start Today we'll start Perceptron, which is a linear classifier. Till last class we have covered k nearest neighbor classifier, which is not linear, and you know why I'm saying non-linear. Non-linear means decision boundary is not linear, but it's according to distribution of the data. So it can have curves, and it could have straight lines, and then again curves. So it's not linear. But Perceptron is a linear classifier, and you will see why I'm calling it a linear classifier. So this is the structure of today's lecture. So before starting anything, I will briefly go through why Perceptron is important for machine learning students. Then we'll see a little bit of history of Perceptron algorithm. We'll see formalization of Perceptron algorithm, how we can formalize. Then we will see Perceptron learning algorithm through which Perceptron learns decision boundary or weights of decision boundary or hypersurface. Then we'll solve one of the example using same Perceptron learning algorithm, and then we'll visualize how hyperspace or this linear classifier tilts to find classifier that can separate data from two different classes. For today's module, I am referring three different books, and books are again same which I have referred for k nearest neighbor classifier. So you can just go through Tom Mitchell's text, Duda's text, but I really like this text, Theodoridis. This text really explains concept of perceptron really well, and it has problem set as well, which will help you to understand perceptron better. So why perceptron? So when we were doing k nearest neighbor classifier in last class, we know that k nearest neighbor is a strong classifier and can achieve good results if number of training samples n are very large. And this is one of the problem I've also given you in the last class to find error bounds. And the thing is, if n goes to infinity of or n is really large, k nearest neighbor classifier will induce at most two times errors to base optimal classifier, two times base optimal classifier errors, which is the best classifier we can achieve. So we know that k-nearest neighbor classifier is really robust if number of samples, but this is restrictive as well. And you know why? Because we know that there is no training complexity for k-nearest neighbor classifier because there is actually no training, it's just storing of data. But test time complexity scales linearly with number of samples and their dimensions, curves of dimensionality. So before I told you that if n goes towards infinity, k nearest neighbor is really a strong or robust classifier. But this is restrictive as well because this test time complexity scales linearly with the number of samples. So it's very bad because you want to add more and more data to have less error. But as you add more, your test time complexity will increase linearly with the number of samples. So this is not, and the result is k-nearest neighbor classifier is really slow for practical example because k-nearest neighbor classifier is calculating distance from test query point to every other point in the data set. Even if we do KD trees, in worst case scenario, it has to traverse through all the samples. So this is very restrictive. And for most of the practical application, test time complexity is very important because we don't want a user to wait for 1 week to predict on test data. So it should be very fast, and KNN is not good in that sense. So you can think of like if you receive Google or Gmail email, and this Google spam filter takes 1 week to deliver email into your inbox because it is going to label it either as spam or not spam. So this is not really we don't want this to happen. So test time complexity is very important, and we want really robust classifier, but at the same time very fast classifier in terms of test time complexity. So KNN is not good in that sense. And the reason is that there is no training actually. So before starting to look into perceptron, we'll look into history, and because history is very important or it's very interesting for. So this algorithm was proposed by Frank Rosenblatt. He was working in Cornell University at that time in 1958. And this is also called first artificial neural network or perceptron. Perceptron is name given to neuron or artificial neuron. And it was intended to model how human brain process visual data and learn to recognize objects. We'll see what I mean with this sentence. But this is important. This is the press conference that US Navy, who was funding that project, gave this statement. The embryo of an electronic computer that expects will be able to walk, talk, see, write, reproduce itself, and so this is actually most of the traits of AI system. And with this one algorithm, it was so much hype that they thought that this one algorithm would be able to have really artificially intelligent, it can build artificially intelligent machines. But this was the hype. And in 1969, after almost 11 years of inception of perceptron algorithm, it was proved that perceptron could not be trained for non-linearly separable data or a XOR problem. XOR is not linearly separable data. I will show you in the slides what I mean by XOR problem or non-linearly separable data. But in 1969, it was proved that perceptron cannot learn non-linearly separable data, and this led to a decade of what we called AI winter. Because with just one paper, most of the funding was dried up. There was no more funding left in AI because most of the funding agencies thought, okay, we thought that perceptron is the best algorithm, but this is not going to happen. So it's better to stop funding such projects because this is just hype. And with just one simple example of XOR, they showed that perceptron is not good and artificially intelligent machines are not possible. So hype was dried down, and even it was like era of succession, or it's winter. Winter means everything is in the stores, so nothing was working, nothing was. So this is very interesting. Is history regarding AI, perceptron, artificial neural network, and if you're interested, you must read it. It's very interesting. Okay, now coming back to perceptron algorithm. Perceptron algorithm assumption is pretty different from what KNN algorithm assumes. Perceptron algorithm assumes that there are, like, these are two samples from two different classes. So you can see crosses. Let's say this is negative class, and there are some green oval shape or balls, and you can see positive. You can say these are positive class. So this perceptron algorithm assumes there are two classes. So this is a binary class problem, and it assumes there's a hyperplane that separates these two classes like this. So this is the inductive bias or assumption that perceptron algorithm makes initially, and which is that there must be a hyperplane, and if there is a hyperplane that separates this data set linearly separates this data linearly, perceptron algorithm is sure to find such hyperplane that separates this, right? So again, perceptron assumption is very different from k nearest neighbor assumption. Nearest neighbor assumes that nearby samples should have same labels. But perceptron assumes that if data is linearly separable, like this, I am drawing it again. So there are crosses, there are zero. Perceptron algorithm makes sure that it will find a separating line that separates this data. So this is assumption of perceptron learning algorithm or percept. Any question up till now?
No, sir.
Okay. But this assumption seems crazy initially if you look at it, because In real life scenarios, data usually is mixed up. Like I am giving you one example over here. This is like hypothetical situation that we will always find data which is linearly separable. So you will find data like this. So there are this samples from one class, but there is cross over here. So this data seems not linearly separable because you cannot find a line or a hyperplane that separates this data linearly, right? So this assumption seems crazy to me initially if you looked at it. But if you remember, when we were doing curse of dimensionality topic in k nearest neighbor classifier, we showed that if data is in high dimension, most of the data lies on the edges of the surface. So when we were looking at the example of cube, a unit cube, and we draw a smaller cube and we wanted to know how much this smaller cube would be if nearest neighbor at 10, we knew that very quickly all the data points were squashed towards these edges or surfaces. So we knew that the surface in between or the center surface in that cube was kind of empty and all the data points were at the edges. So if the data is in high dimension, this assumption almost holds that data is linearly separable. In 2D spaces, which is low dimensional space, this assumption probably would not hold for a long. But if your data has high dimension, let's say 20, 30, 40 dimension, dimension, this assumption almost or most of the time holds that data is linearly separable, and I will show one of the example in my slide. And in no dimensional space, if linear separability doesn't hold for long, in high dimensional space, it almost hold. And there is a trick called kernel trick. If your data in low dimensional space is not linearly separable, with this trick, this is mathematical function. If you can define such function and you map your low dimensional data into high dimensional, even non-linearly separable data becomes linearly separable data in high dimension. And actually, this is what we do in support vector machines. They have different kernels and they map into high dimensional space to find linearly separable plane. So in essence, perceptron is opposite of k nearest neighbor classifier as KNN works better in low dimensional spaces. Remember curse of dimensionality, right? So it works better in low dimensional spaces. While perceptron assumptions hold only or most of the time only in high dimensional spaces. So KNN works better in low dimensional spaces and perceptron algorithm works better or is assumption hold in high dimensional spaces. So in that sense, K nearest neighbor classifier and perceptron are just opposite, right?
Right, sir.
Okay, so this is what I mean to say. Here is the ZOR problem. I mentioned ZOR problem 2 times in this lecture. This is the truth table of ZOR. ZOR is a really interesting problem. It gives output when inputs are different. So 0, 1 is 1 and 1, 0 is 1. And then outputs is 0 if inputs are same. Really, we knew that. And if you plot ZOR in 2D, it looks like this. This is in front of you. So this red dots belongs to class 1 or positive sample because 0, 1 is 1 and 1, 0 is 1. And if it is 0, 0 or 1, 1, it will be 0. So these are two classes. And we know that we cannot find a hyperplane that separates this data because if we draw hyperplane like this would be misclassified, this sample. If we draw hyperplane like this sample would be misclassified because this is with these data points, with plus data point. So this data is not linearly separable in 2D. But let's say if I plot the same data in 3D, what will happen? Now, this is like a small visualization. Some images, I have stacked up images to show you a video. So now I'm plotting it in 3D. So now these points have moved over here. Probably this is visible to you guys. Now look at it. Right? This is the same ZOR data in 3D. I have added third dimension and I'm showing you with just adding one dimension, this data become linearly separable. You can find infinite number of hyperplanes that can linearly separate this data in 3D. In 2D, XOR data was not linearly separable. There was not a linear surface that can divide samples from one class to another. But in 3D, it's very easy to see that this data becomes linearly separable. And if you want to see the same video, I have given you YouTube link. You can see this visualization how from 2D to 3D this data becomes linearly separable. So it means that if we map our data to higher dimensional space, it becomes linearly separable. And perceptron algorithm that guarantees that it would find a linearly separable hyperplane. Again, this is the visualization how 2D data becomes separable in 3D data. So in 2D, this is the data sample. Right? So data are jumbled up, and we know that we cannot find a line or a surface that divides red samples from green sample because this is kind of a circular, this kind of a data. KNN would find this kind of a boundary, but perceptron cannot find this boundary because it's looking for a linear surface. But now look at it. I say kernel. Kernel is a mathematical function that will map this data to higher dimensional. And if we plot the same data in 3D, like I did for the Zohar problem, this data becomes linearly separable. So again, the same visualization. You can visualize how in 3D this becomes linearly separable. So in 3D, this becomes like a pyramid, and you can find a hypersurface which is shown over here, which can divide sample from one class to another, right? So this is very intuitive, and initially it seems very interesting to see how data becomes linearly separable in higher dimensional space. So there is a little trick that can be done to transform data, change data point without changing its data values in such a way that it becomes linearly separable. Define a function. This is called kernel. If you read text, you will find kernel tricks or kernel classifiers. So this is actually the kernel that will take data point and change its dimension. And the idea is if you go into higher dimensional space, you will find a linearly separable classifier. Now coming back to perceptron algorithm. I have shown you the same data set before now, but I have more details now. So this is, we can visualize this perceptron classifier. So there are these two samples from two different classes. So reds mean negative example, green mean positive example. And this is the hyperplane that perceptron has found that divides these two samples. And this hyperplane can be defined by a vector W. So hyperplane is normal to this vector W. So this is the vector, let's say W, and this is the classifier which is perpendicular or normal to this W. And it says that this is again hypothesis. If you remember my initial classes, I say that we can call classifier as hypothesis as well. So H is superclass of hypothesis, and we are looking for small h, let's say. And perceptron is kind of classifier, is a set of classifiers for all x such that W transpose x plus B equal to 0. So this line or this W vector or this hyper classifier is defined by this mathematical equation, which is W transpose x plus B. I will explain what I mean by this. So W is weight vector for this vector. It's weight vector, right? And all the samples from one class lie on the one side of this classifier, and all the other samples from other class lies on the other side of the classifier. So on the right, or we can say that the sign of W transpose x plus B is positive, or this sum is greater than 0, and over this side W transpose x plus B is less than 0, or sign is negative of this expression. I will explain you this further so it will become easier for you to understand. Assuming that hyperplane exists that linearly separates data according to label, perceptron algorithm tries to find it. But again, same. Mathematically, hyperplane can be given by W transpose x plus B equal to 0. So if W transpose X plus B is greater than, it means sample is on positive side. If W transpose X plus B is less than 0, it means sample is on negative side. And if it is W transpose X plus B equal to 0 for any sample, it means sample lies on this classifier line. That's it. So W transpose XB, where B is the bias term. Without bias term, hyperplane that W defined would always go through origin. If there is no W, this hyperplane would be like this from origin over here. So W defines tilt or angle of this hyperplane, and bias is how far it is. Right? It's like if you move W, this hyperplane would be like over here. If bias is in negative, it could be like this. So W defines how is the offset actually. W is the offset, and sorry, B is the and how far it is goes, and W vector defines its gradient, its angle, right? Its tilt, right? Any question up till now?
No, sir.
Okay. So learning algorithm that we haven't seen till yet will learn W based on the data set we provide. So this is how we define a classifier. The only thing we need to find W. What would be W vector? Because X is our training samples. So if we define a hyperplane, a classifier with W classifier, what to do at test time? So training is done. Let's say if we have trained and we know that this is the classifier and we know W's. So at test time, we will just solve this equation, and I told you before, and we look at the sign. And what I mean by sign is over here. So for all the x's in class 1 or for all the sample in class 1, W transpose X plus B is greater than 0 or sign is positive. I have seen this, look at the sign. So over here, all the samples, for all the samples, this W transpose X plus B is positive, and vice versa. For all the samples on the other side, for negative samples, this W transpose plus XB would give minus sign. So this means test time speed is constant. It is very fast. It is very fast. Right? So test time complexity here, if you just compare with k nearest neighbor classifier, test time complexity was huge. It was linearly scaled linearly with the number of data points. But here, once we train this classifier, at the test time, it is just one calculation which is like could be done in nanoseconds. So test time complexity just reduces exponentially in such classifiers. Right? You just have to do this multiplication or dot product of and see their sign. So this is in nanosecond, that could be done in nanosecond compared to KNN algorithm, which probably would take a day or two to just predict one sample if your data set is huge. But there is one problem in previous equation which I was showing you, W transpose X plus B. So in this equation, algorithm has to learn weight for W and offset B. So this is gradient W, gradient vector or tilt of our hyperclassifier, and B is offset. Okay. So for given data set, algorithm has to find these two terms. X is input vector or input samples. So dealing with B separately is difficult. Difficult mathematically for different proofs that we will do in this lecture, and difficult for programming because we need to keep it updated. Like in each loop, you will see what I mean in each loop. But in each loop, you have to update W and B separately. But with this just one mathematical trick, we will merge this B into W, and this whole equation will become W transpose simply. What we'll do, we'll add 1 into our vector or training vector xi, and we'll add b into w vector, right? So w becomes this vector w and b. So w is actually merged with b. In this vector we will find value for W and B together because we have added 1. So dimensional remains same. In some books you will find B as written as W naught as well. So if you read a text or a book, you will find probably W naught as well, but if you see W naught, it is offset B. Right. So we can verify if we do that. Now this is X, this is W, and you can see that their value remains same. If you just multiply these two terms, we will find the same thing which I have given you earlier. So there is no difference mathematically, but for our convenience, we merge W and B together to find just one weight vector, and we will learn just one weight vector from our. Any query up till now? Any question?
No, sir.
Okay. So our training vector becomes xi and 1. So xi is original. We add one more dimension in our data, and w becomes w. So w and b has both gradient and offset. And our hypothesis, which was previously w transpose x plus b equal to 0. This was our equation of hyperplane or a classifier that becomes like this, which is W transpose X because B is now merged with W. So we absorb B with W, and so mathematically there is no difference, but for programming and mathematical derivation, this becomes now easier for us. Now the important thing is to know how we can train this perceptron or this classifier, or how we can find weights for this perceptron classifier. So this is the pseudocode for perceptron learning algorithm. I will explain each line, so there shouldn't be any ambiguity. So we'll initialize W with zeros. So initially our W vector is zeros, right? Initially our vector is 0, so we will make we will make like all samples would be misclassified. You can just think. And now there is a loop, infinite loop, while true. So while true, it means if there is an infinite loop given, and it will break when something will happen, and I'll explain this condition when we'll break this loop. We'll classify misclassification equal to 0. So this is just initialization. We initialize W with 0. We initialize misclassification. So initially there is no misclassification because algorithm hasn't started yet. Now there is a loop for every x, I, y, I. Like for every sample in our data set D. Xi, yi our samples. Remember, xi means our training data, and xi could have number of dimension x2, x3. Remember, this is only one. For sample 1, this could go to xn. So these are dimension for one training sample, and then yi. Yi in perceptron, we are assuming this is binary classifier. So yi would be and -1. This would be our y. So this is our training sample. It could have n dimensions. So for every training data, and we will do this loop. If yi w transpose x is less than equal to 0, you just have to understand this line to understand this whole algorithm, perceptron learning algorithm. Can anyone tell what this means? If yi w transpose xi less than equal to 0, any idea? This, if you don't know, I'll explain. This means this is a misclassification. And I will explain why I'm saying that this is misclassification. Initially, W transpose X plus B is greater than 0 for positive examples. B is not over here. This is W transpose X because B is merged. Sorry. So W transpose X is greater than 0 for all yi's which are positive 1. So even if we multiply according to this equation plus 1, yi is plus 1, this remains true. So this is for positive example W transpose yi, W transpose X is greater than 0. And if it is negative sample, this yi is minus 1, W transpose X is less than 0. This is our initial equation, and if we multiply minus 1, we will know that this would become W transpose X is greater than 0. Right? So this is for positive samples, we can write like this, and this is for negative samples. So we know that this is equation is same. If we just multiply with yi, W transpose X is greater than 0 for positive and negative. It means if it is less than 0, less than equal to 0, it has misclassified. So this is to say mathematically that misclassification has happened. So if misclassification happened, algorithm will update W vector because W is not correct. So and W is corrected like this. W equal to W plus, so you will add W, you will add X into W. So it simply just says if you have misclassified X vector, you will add that vector into W. This is times Y, X is multiplied by Y. So you will add if has happened for positive class, and this would be subtracted in W if misclassification has happened in negative class. So it means W's product or inner product, because it's W transpose X, would be you want to reduce for negative classes. So if we reduce W, it means that inner product would be less, and we want to make W in such a way that next time that misclassified sample is classified correctly. Once I will visualize this with you guys, you will understand how this W is updated. But mathematically, this is how we'll write it. Any question up till now? Any query?
No, sir.
Okay. So there is a loop for every data point in a data set. We will check if misclassification has happened. If misclassification has happened, we will update our classifier because classifier is not correct, and we will add 1 into misclassification. Before misclassification was 0, we will add 1 into it. So this is inner loop, and we'll break this loop if there is no misclassification anymore. So it means we have find correct hyperplane that each and every sample is correctly classified, right? So this algorithm will keep on looping on the data set till all the samples are not correctly classified. So if this is our data set, let's say, if this is the classifier initially you find, it means there was one error over here. In next iteration, it probably will shoot, it will go over here, and after that it will find a classifier. So once a classifier is found and each and every sample is correctly classified, it will break and we will get W updated. And that W we will use for predicting unseen data. Right. So this is the notion of perceptron learning algorithm, or how we can just train this perceptron classifier uh, to find perfect weight vector. So in algorithm, again, I am explaining this term that misclassification, although I have explained this over here, but I'll explain again. This statement is written, and remember again we are dealing with binary classifier, and W transpose X is greater than 0 for positive sample and W transpose X is less than 0 for negative sample. And by combining equation 2 and 3, so if 2 and 3 we can just write it like this, जो मैंने आपको पहले ही बताया था, this is what I have told you before. The proof is if you just substitute plus 1 and minus 1, you will find original equation, right? So y1 is plus 1 for positive sample, and if you substitute plus 1, you will find this equation. So this is true for positive sample. If you substitute -1 over here, we will get this sample, this equation, which is true for negative over here. So we know that if we combine these two equations, we can just write this one equation to say that this is correct classification. And if it is less than 0, it means that misclassification has happened, like over here. So if it is less than or equal to 0, it means 0 misclassification has happened, because we can write it like this. This shouldn't be equal. This is greater than 0. So it means that this is correct classification. So again, in Perceptron algorithm, this statement refers to misclassification. This shows a misclassification because correct is greater than 0. This is how we can write for correct. And this is called update rule or Perceptron weight update rule, which I have explained you earlier. So W is hyperplane that has created or induced an error. So we want to update it, and we will update it by adding an instance which is misclassified. So this misclassified instance would be added in W if it belongs to plus class, and this instance would be subtracted from W if misclassification has happened in negative class, because we are scaling it with y, and y is either +1 or -1. So sign would change classes. Any question up till now?
No, sir.
Okay, so I'm explaining again over here. If misclassified sample belongs to plus class or +1 class, that W amount add in W amount proportional to misclassified vector x again over here, because y is +1. And if misclassified sample belongs to -1 class like this, it would be subtracted simply. And this algorithm belongs to more general algorithmic family known as reward and punishment schemes. So this algorithm belongs to this class of algorithm, reward and punishment algorithms. This is just a name. So now this is one of the example which I am solving you, and to show how W vector can be trained. So consider 4 data points: -1, 0, 0, 1, 0, -1, and 1, 0. So these 4 is our data set. This is our data set. And we want to build a perceptron classifier for these 4 points in our data set, D. And we know that initially W vector is 0. Here you will see the dimension is 3 because B is merged in W, and we'll add 1 over here. So this is vector. Remember, we say xi would become xi and 1. So we'll add 1 and this will become 3-dimensional x vector as well. And these two are W1, W2, and this is W0 or B. So consider the first data point, -1, 0, 1. So -1, 0, and we added 1, right? Because we are merging W and B. And we'll find W transpose X. When we'll do W transpose, this is W transpose because W is 0 initially. And this is our X vector, and we are finding dot product, and dot product is scalar. That becomes equal to 0. And this is misclassification because this point belongs to +1 class, and this should be greater than 0 to be correctly classified. It means W needs to be updated because it has done an update rule. As we know it earlier, it's W is equal to W plus YX. So if we just substitute values over here, W equal to W plus YX. So this is W, Y and X. This is Y is +1 because the sample belongs to +1 class. This is X, and you solve it and you will find this updated W. So our W initially was 0, 0, 0, and after one, it encountered one misclassification. It's updated to this weight vector. Now we'll consider second data point, which is 0, 1. If you see 0, 1, but we'll add one more dimension in your data, one, and we'll again do the same calculation W transpose X. Now if you do W transpose X, this is greater than 0, and this is correct because this sample belongs to class W1 and W transpose X should be greater than 0, and this is correct. So we don't need to update. Our W remains same. This remains same because W doesn't need to update over here. Now we'll consider third data point. Again, I have added one. This is third dimension over here. We will W transpose X. And if we do dot product of W transpose X, we'll find is equal to 1 and which is greater than 0. But this sample belongs to class -1 or negative class, and this result should be less than 0. So it means misclassification has happened. So we need to update W. Again, this is the update tool. So W, this is W, Y is -1 because this is sample from negative class, and this is misclassified X. We'll solve it and we'll find this updated W. So this was W before start of this iteration, and finding one misclassification from negative class, this vector is updated to this W. So you can see that W is updating itself or tilting, and its offset is being changed to find better hyperplane that separates data. Now we'll do 4 data point. This is this is correct because this belongs to class -1 and W transpose X should be less than 0. So this is correct, and no, we don't need to update W3, and W3 remains same. So this W remains same for all the data point now. So now all the 4 data point has been iterated through because our data set has 4 points, but we have misclassified during the main. If you remember the classifier, it will keep on running till it will run again on the complete data set to know if there is any error. So this we have to go through again this loop again for all the xi and y's to find if there is any misclassification left, and we will just stop only if misclassification becomes 0 in this iteration. And in our example, in this iteration we have done at least 2 misclassifications, so we have to run these statements again, this loop again. This is clear?
Right, sir.
Okay, so one loop on data set is completed in which misclassifications were encountered. So we have to run it again through again the data set. So this is first sample again. We'll find W transpose X. Now this is updated W which we have. We'll run it and we'll find that result is okay. W transpose X is greater than 0 for positive. So this is 0. Now consider second point, we'll do it again. We know that now W is again okay because we are getting W transpose X greater than 0. Third sample, again correct. So it means this W is correct. For last 4 data points, there is no update, and it means that final weight vector is this. So with one simple algorithm, we'll find a hyperplane or line that linearly separates the data. And we started from 0, 0, 0, and we ended with this weight vector. And this weight vector has a gradient and offset for a separating hyperplane. Right? Any question, guys?
No, sir.
Okay. So this is resulting linear classifier that places all the data points, and this line has slope 1 and intercept 0. So this is something like 1, 2, 1, 2, slope 1, intercept 0. So this would go something like this. Actually, this should go over here. Slope 1 means that slope is 1. Okay? So this is that kind of line. But I am asking you how I know that slope is 1 and intercept is 0. Do you have any idea how to find slope and intercept from this weight vector? You have to read through the book of Diodorus to know how to calculate slope and intercept for such lines from this W vector. This is very intuitive geometrical derivation and it's easy to understand. So this is probably, if you want to know it more in detail, you should do it. And this is given in Diodorus book. Now I'll visualize how W is getting updated. Okay, so let's say this is the current hyperplane that we have that is separating the data point, and this is W vector. So W vector is given over here, and the line perpendicular or a normal line that is separating the data points is shown over here like this. And let's say we have encountered a misclassification, this point, because this point belongs to plus class, but it is now at the moment lying at the negative class side. Actually, the classifier should be over here somewhere. So this point should be on the right side of our classifier and its sign would be +1. W transpose X should be +1. So once we update, what will happen to this classifier? Update rule is given by W equal to W plus YX. So this is geometrically just addition of vectors. And we know how we can add vector. Let's say if this class is misclassified and we are solving for this, this is our W vector. We want to add, this is X vector, and we want to add it into W. This would be resultant vector, something like this. So W vectors become like this, and our hyperplane is updated in this direction. So now this point is correctly classified. Initially we started from this classifier and we were misclassifying one point. After update, this becomes like this. In our example, after an update, X data point gets correctly classified, but there is no guarantee that after one update data point will be correctly. In this example, it is correctly classified, but in real life scenarios, there is no guarantee that after an update that point would be correctly classified. And I want you guys, this is your homework, to let me know how many times a point can be encountered with misclassification. There is one bound that one point can be seen at most that number of times by a classifier. After that, it would be correctly classified. So please go and do this homework and submit it to me offline. Any query up till now?
No, sir.
Do you understand homework? Did you get the homework?
Right, sir.
Okay. I have a MATLAB demo as well for you guys. I'll try to run it during the class as well. But some of the results I have placed in my slides as well. So let's say if you're given these two data points, this is OR problem, if you remember, kind of. No, it's not OR because it's linearly separable. So these are the four data points. Actually, these are the points which we solved by hand in example. And if I run it, I have programmed this perceptron learning algorithm. Initially, perceptrons find something like this, but even after second iteration, it finds the line that separates data points correctly. So it just checks again because algorithm has to run one complete time without misclassification. This is correctly classified and this finishes. Now again, this is another demo. This data set is a bit more complex than the previous one. Previous we just had 4 points, 2 from each class, but now we have 5 sample points from each class, and they are bit arbitrarily placed in the space. And if you run it, this algorithm, it finds initially everything is misclassified. Vector gets updated, and we can see that okay, it is coming towards our data points. Before it was just way away from the data points. Now after updating, this just overshoots. From here, all the points are on the right side. After one update, all the points is on the left side. You are understanding this demo? Are you getting any query from the demo?
No, sir.
Okay. So this is after third iteration. After fourth iteration, again it goes back. So this is like overshooting, because there is no learning step involved in this perceptron learning algorithm. This is 1958, so it's not very sophisticated. But now after fifth iteration, it is finding it's coming towards a classifier that can classify. Sixth iteration, seventh, eighth, and it's done. So it has find a classifier that can classify all the data points correctly. So I'll try to run this demo for you guys. If you can see, let me see if I can run it. If this MATLAB window is can you see this MATLAB window?
जी sir, visible है.
Okay, so I am drawing first. Initially, I will input data points. So where I will click, it will be a data point. So I have entered data point for one class. I am entering data point for second class. Now these are the points. Probably my screen is getting hanged. Let me rerun it because let me try it again. Samples from one class, samples from second class, data point. Okay, now you can see in real time. Right, you got the intuition?
जी sir.
Can you code it by yourself? Can you code it? I'm not getting any answer.
पॉसिबल कर सकते हैं सर. जो हमने पहले कोड देखा था, जो पाइथन कोड था, तो
Right.
वो उसी मतलब क्या क्या उसी टेक्निक तो वही रहेगी ना, मतलब सिर्फ लैंग्वेज का फर्क है ना, राइट?
In this for Perceptron, I haven't used any library. For initially for my Python code, I was using scikit-learn library. But for this algorithm, I have coded Perceptron algorithm. The same algorithm I have shown you in my slide. Like, let me show you this algorithm. I have coded this algorithm. It's pretty simple. It's just in 10 lines of code. You can just code it.
सही.
This is not difficult. So I coded myself. So there was no library involved in this demo. And for previously for Python, I use sklearn or scikit-learn for the demo purpose. And that was in Python, and this is MATLAB, but this doesn't make any difference. You can just code it in Python or MATLAB, your favorite library, if you want to see. But this is how it is done, right?
Right sir.
And this is initially I showed you that perceptron is also called as artificial neuron. And whatever we have done, we can just show it as a neuron. What we have done, we took all the inputs. These are our inputs, input vector. That we are multiplying or dot product with w's. This is weight vector that we try to learn. We sum them up because w transpose x, so each x is getting added together. We add the bias term and we just pass it through a function that tells whether it's +1 or minus 1. So this just gives a sign, and this is in literature called so-called like activation function. So whether neuron is active or deactive, whether neuron is firing or not firing. So this could be shown that perceptron is this kind of learning machine is artificial neuron, because in neuron we have almost same steps. We have synaptic connection if we just talk about in terms of neurology or how our brain works. So we have synaptic weights, W transpose X again. We are doing this W transpose X. We are summing them up like this. Then there is activation function which gives us sign whether it's +1 or -1, and we have the output. So this is why this perceptron is also called as a unit neuron or artificial neuron. And if we add multiple perceptron, it become multi-layer perceptron. If we add perceptron in different layers, so let's say we have input layer of perceptron, then we have another layer of perceptron, then we have output layer of perceptron. So this becomes multi-layer perceptron. But learning machine is same, which we have done. Learning algorithm, there could be different learning algorithm, and we'll see when we'll do neural network. But this is like a building block for artificial neural network.